The prime numbers, the number which is divisible by 1 and itself. In the last we have AK into MK inverse. We take the value A for the quadratic congruence. NB is the number of bits in a value X. Hello students, welcome to the next session of network security. Let's start this session. The fundamental theorem of arithmetic is that we can use the set of integers to perform a exponentiation or factorization. Factors is nothing but multipliers of a number, isn't it? So if you have a number 10, so it can have the factors 5, 2, where you can get 5 into 10, or 10, 1, 10 into 1, isn't it? So these are the factors of the number. Factors is nothing but reduced expression of a number, isn't it? So what factors we have is 10 has the factors 5 or 2 or 10 or 1. These are the factors of the 10 or factors of a number. In this, we are going to know about the factorization. In factorization, we have an expression where we use the prime numbers and the non-prime numbers. Prime numbers may be, you know about the prime numbers, the number which is divisible by 1 and itself, isn't it? All the other numbers are non-prime numbers. Okay. Here we use two expressions. One is set of primes, another one is E, set of integers. E is set of integers you can use. The set of integers can be expressed, or the factorization can be expressed as factors of multipliers. If n is a number, how do you represent the factorization of that number is using the primes or prime numbers. So if P1 to Pn is the set of prime numbers and E1 to E2 is the set of integer numbers, set of positive integers, you can represent n equals P1 to the power of E1 into P2 to the power of E2 into up to Pk to the power of Ek. You can use this expression. This expression can be used to find out the greatest common divisor and the least common multiplier. Here we have A equals P1 to the power of A1. So A1 is the set of numbers, positive integers. P1 are the set of prime numbers. So you can find out the GCD of two numbers A, B. The expression can be P1, that is prime 1, to the power of minimum value of A1, B1. So we take A1, B1. From A, B, we take P1 of minimum A1 and B1 into P2 of minimum value A2 into B2. So we go on calculating up to P of K, that is AK and B to the base K we use. Okay. This gives the GCD of or greatest common divisor of two numbers A, B. Factorization expression can be used to find out the LCM also. Here we have the expression. For LCM, we make use of maximum value. For GCD, we make use of minimum value. Okay. So you can relate the LCM and the GCD using this expression. LCM of A, B into GCD of A, B will give inverse of A and B. So they will be inverse of each other. Okay. The factorization can be carried out with a format method. We use a format expression to find out the factorization of a number. You can use this expression to find out the factorization, which is called as the format method of factorization. So n equals x square minus y square equals a into b, with a expression as x plus y and b is x minus y. You can calculate the factors of a number using the Fermat method. Here we have the algorithm for our pseudocode for Fermat factorization. Here we have the parameter which is passed as n. N is the number to which factors must be found out. N is the number to be factored. Then we have x. Square root of n is calculated, which is assigned to x. It is the smallest integer greater than square root of n. Okay, while x is less than n, so we shall go on repeatedly finding the square which returns a comma b. So a comma b can be used to find out the factors of the number n. Okay, this is the pseudocode to find out the factorization using Fermat method. Then we have another method, that is polar p minus 1 method. So here we have the expression p equals GCD of 2 to the power of b factorial. We use b factorial, b into b square like that. So is GCD of 2 to the power of b factorial minus 1 comma n. You can use this expression also to find out a factors of a number. So here we have the pseudocode for finding out the factorization using polar p minus 1 method. We use the parameters n comma b. N is the number to factorize. B is the power of 2, that is factorial value that needs to be calculated. So we get a and e as 2. A is the set of prime and e is set of positive integers. While set of positive integers is less than b, that is 2 to the power of the 2. If it is less than power of the 2, the calculation will be done with this expression which calculates the factors of a number n. We have the improvised method of Pollard method, that is Pollard row method. It uses a mathematical row equation for the successive numbers. If you have successive numbers to which factorization must be done, factors must be found out, we have to use this method, that is Pollard row successive numbers. Okay, here we use starts from x1, x2 to xi plus 1, I plus 2, I plus j plus 1. Set of series of numbers will be used which calculate the factorization for the Pollard row method. Here we have a pseudocode for Pollard row method. So we use the same parameters, that is n is the number to factorize and b is the another set of primes. We can use the x, y and p values are used. We use the expression x1 minus x2 equals q into p. We'll calculate this expression using the p value. While p is equal to 1, that is prime value, we are going to execute these expressions to find out, and we use an expression GCD of x minus y comma n. If p is equal to n, the program has failed. That means the n is prime value, that is 1. You cannot find out a factor for 1, isn't it? So 1 doesn't have any factorization, 1 and 0. So there is no factor that can be written for the value 1 when p becomes equal to n, because p is assigned the value 1. So if the n is equal to 1, there is no factors to be defined. Otherwise, you can calculate the factors using these expressions and you can return p. Here, instead of n is given for the function as a parameter, the final output is p. P is the set of prime. We calculate the factor of n in Pollard RHO method for the prime numbers. Okay. Then we have some more efficient methods that can be used to find out the factorization. One is the quadratic sieve. This method uses a sieving procedure to find the value of x square mod n. So we have the expression, sieve method has the expression O of e to the power of c, where c is equals the logarithmic value of n to the power of half is used to find out the method or find out the factors. Then we have number field sieve. Here the method uses a sieving method procedure in an algebraic ring structure to find x square congruent to y square mod n. So you can use this method to find out the factorization, which is much more efficient and executes more efficiently than the previous methods. This is about the factorization. Next we shall move on to the next concept, that is the Chinese remainder theorem. What is this Chinese remainder theorem is? So it talks about the congruence operation in the remainder. We know about congruence is all about using the modulus operation, isn't it? So the Chinese remainder theorem is used to solve a set of congruent equations with one variable. A single variable is used with all the congruent equations, but there will be different moduli we can use which are relatively prime, which are prime in a set. We can use the expression like we use the single variable, one variable x with other number a1, a2 to ak with different moduli. We use the expression Chinese remainder theorem. The following example of a set of equation we have is x congruent to 2 with mod 3, x congruent to 3 with mod 5 and x congruent to 2 with mod 7. That means the moduli are different, the values are different, but you need to have a single variable which makes the congruence of the value with different moduli. Okay. The solution you can get is to this set of equation is given in the next slide. For this moment, note that the answer to this equation is x equals 23. By calculation, we draw the value of x, that is x equals to 23. If you divide 23 by 3, you will get the remainder 3. If you divide this value satisfy all equation, 23 is congruent to 2 mod 3. So we have the 23 mod 3 will give you the value 2, whereas 2 mod 3 also gives you the remainder 2. When you have 5, 23 mod 5 gives you 3, 3 mod 5 also gives you 3 only. So 23 mod 7 will give you 2, 7 3 is a 21, so you'll get 2, 2 mod 7 also gives 2. So we have the moduli, different moduli for a single variable which calculates the remainder. This is called as the Chinese remainder theorem. The solution for Chinese remainder theorem is step by step. We have to find the m with m1 into m2 into mk. This is set of moduli we have used. m1, m2 up to mk. This is the common modulus we get by multiplying all the different modulus. Find m1. How do you find m1 is m by m1 first moduli. m2 equals m by second moduli. Like that it goes on up to mk equals the common modulus by the last moduli. Okay. The third step is find the multiplicative inverse of m1, m2 to mk. That is this one, m1, m2 up to mk. Find out the multiplicative inverse using the corresponding moduli only m1, m2 to mk. We can find out. Call the inverses m1 to the power of minus 1, m2 to the power of minus 1, mk to the power of minus 1. Now, the last step is the solution to the simultaneous equation can be obtained by x equals a1, that is the A1 is the value that we use with the congruence. Okay, A1 into M1 into M1 inverse plus A2 into M2 into M2 inverse. In the last we have AK into MK inverse with mod M gives you a X value. Okay, so here we have the example. So here we have the expression that can be used to find out the X value using the Chinese remainder theorem. Then we have another concept known as quadratic congruence. We know about the congruent operations, isn't it? So we are applying that congruent operation to the quadratic equation of a square x plus b square x plus c equals 0. So this is the quadratic equation. Same quadratic equation will be applied with congruence operation. So we have so many applications of quadratic congruence in the cryptography. In cryptography, we also need to know about the quadratic congruence, that is equations of the form a2 into x square plus a1 into x plus a0 is congruent to 0 with mod n. Equation we use in which a2 equals 1 and a1 will be equal to 0. The equation will be of the form x square equals, if you make a2 1 and a1 0, you will get x square plus a0 equals 0. If you take to another side, so x square will be congruent to a of 0 or simply a mod n. You can calculate like this. A to the x square plus a1 into x plus a0 equals congruent to 0. If a2 becomes 1, 1 into x square plus a1 is 0, 0 into x plus a0 is congruent to 0. Now we have this becomes 0, x square plus a, since there is only one value, no need of specifying the 0. X square plus a congruent to 0, or you can take it as x square congruent to a mod n. Even though the sign will become negative, since the congruence takes for only the positive integers, we take the value a for the quadratic congruence. Okay. For this, we use Euler's criteria that can be used. We use the concept of Euler's theorem here. The Euler's criteria with the quadratic congruence will be if a into a to the power of p minus 1 by 2 is congruent to 1 with a modulus moduli p, a is the quadratic residue of modulo p. We have the quadratic residue or quadratic remainder you can take of modulo p. Okay, if a to the power of p minus 1 by 2 is equal to or congruent to minus 1 with mod p, a is a quadratic non-residue of module p. So residue and non-residue. Residue is when a number has more than one solution, more than one factorization. Non-residue is one when you don't have any solution for the number. So if it becomes negative 1, a is the quadratic non-residue of module p. If this expression is congruent to 1, it will be the quadratic residue of modulo p. Okay. So when solving quadratic equation modulo a prime, we use the special case p equals 4x plus 3. Using this special case, you can draw the expression x congruent to a of p to the p plus 1 to the power of 4 mod p and x equals minus a. Plus and minus, positive and negative numbers are taken for finding out the congruence on a x and y direction. Next, we shall look into the exponentiation and logarithm. As we know, exponentiation and logarithm are inverse of each other. Okay, so exponentiation uses the expression y equals a to the power of x, whereas logarithm uses the expression x equals log y to the base a. So they are using exponentiation using the power, whereas logarithm uses the base. Okay, the thing is both are inverse of each other, like our encryption and the decryption. So we have an exponentiation method. For fast exponentiation, we use the square and multiply method with this expression y equals a x to the base nb minus 1 into 2 to the power of nb minus 1. So we use both the base and the powers to calculate the exponentiation with the xi equals 0 or 1. So we use the examples. So we use this expression to find out the exponentiation. Like we have an example, y equals a to the power of 9 equals a to the power of 1001 with base 2, that is the binary value. 9 is represented as 1001, which can be factorized with the value a to the power of 8 into a to the power of 0 into a to the power of 0 into a. So we can use this. A to the power of 0 stands for 1, 1, and we have a to the power of 1 equals a. So we are finding the factorization along with the exponentiation in this expression. So here we have a pseudocode for square and multiply algorithm. We are first making the parameters a comma x comma n. N is the value for which exponentiation has to be found out. Y is assigned the value 1. For the value I to 0, 0 to n to the base b minus 1. nb is the number of bits in a value x. So we calculate if xi equals 1, y will be calculated with this expression a into y mod n, that is multiple only if the bit is 1. If it is 0, no need to find out. Then we have a equals a square mod n. Squaring is not needed if it is the last iteration. For intermediate iterations, you will be doing a square mod n. Last will be just a we use. So it returns the y value, that is the exponentiation value in y. Then we have the logarithm, which is the reverse of exponentiation. In cryptography, we need to discuss the modular logarithm, that is with modulo operation. Okay. So exhaustive search for modular algorithm, logarithm will be done like this. So using the expression x equals 1 to n minus 1. So we use the congruence operation. If y is congruent to a to the power of x with mod n, will return x, else we return 0. So k is the number of bits in the x. So we return if there is no value, x is assigned 0, there will be no logarithmic value returned from this exhaustive search method of logarithm. This is about the basic mathematics. We need to know about the asymmetric key cryptography. Thank you.